Swayam Prabha. Digital India. Educated India.
Endpoints. We know the definition of convex hull. So, goal is to compute this convex hull, right, and our target is, what should be a good target? N log n, right. Okay. We will see if we can do better. Now, how many of you are kind of comfortable with lower bounds of problems? Lower bounds of problems. You know that sorting has a lower bound of omega n log n, right. So, any comparison based sort has to do at least n log n comparisons to give you the. So, a lower bound is about a machine model, and so here the machine model is such that it can do only comparisons, and one can show that the problem of sorting has a lower bound of omega n log n, and by a reduction from sorting one can also show that convex hull also has a lower bound of omega n log n. So, if we can achieve this target, then we are doing pretty good. Fine. Now, to start with, let us talk of so tell me of one point for which you are sure that is going to lie on the convex hull. The point with the right. So, we are sure that this is going to lie on the convex hull. One more, rightmost, good. One more, topmost, good. Lowermost. Now, if if it is n log n, I can think of a divide and conquer algorithm. If I am thinking of a divide and conquer algorithm for sorting, now what I have to do is, again like the idea we had in this closest pair problem, that I took a x median line, divided the point sets into two halves. I can compute the convex hull of the left part, I can compute the convex hull of the right part, and then probably I have to figure out a common tangent kind of thing in linear time, such that it bridges these two convex hulls, right. And then possibly you can think of a recurrence like this, right. So, T n is the time for computing the total convex hull. I have taken the x median coordinate, divided the point set into two halves, computed the convex hull here, taking one of these T n by 2s, convex hull of the right part, taking the other T n by 2, and if in linear time I can compute this line segments, this and this line segments, this and this line segments, which are known as, let me call them as bridges. So, if I can compute these bridges in order n time, then I can get the convex hull, right. So, take this as an exercise. So, this exercise is just if you can convince yourself that you can compute these bridges in linear time, then the divide and conquer goes through, fine. So, but let us now forget about this, and let us look for an algorithm of this paradigm. We will try to figure out an incremental algorithm for this problem. So, an incremental problem algorithm is like I will keep on adding points according to some order, and I will try to maintain the convex hull correct up till this point, right. So, I will insert points in certain order, and I will try to maintain the convex hull correct up to the last insertion, fine. And if I can maintain this correctness at each step, then when I finish, I know that I am done. So, essentially my idea would be to start from the leftmost point, consider points in some order to go to the extreme rightmost point. Okay. So, what I do is the first step of my algorithm is get the leftmost point, get the rightmost point. What is the time I have taken? Order n, right, to figure out the point with the minimum most x coordinate, maximum most x coordinate. Let us so, my algorithm step is okay. Now, see, as because I am targeting for an n log n time algorithm, I can do a sorting, right. So, my first step is sort the points according to their x coordinates. This takes a n log n time. Okay. Once I have sorted, it is easy to pick up the leftmost point and the rightmost point. Now, what I do is
all the x coordinates are integral coordinates.
rational coordinates. That is the assumption I started with. Okay. Order of no n log n. I gave you n log n, right. I wrote here n log n. Now, I pick up the from that sorted list, I pick up the leftmost point and the rightmost point. So, the point with the lowest x coordinate, the point with the highest x coordinate. And what I do is I join this line segment and I divide the points into two halves, one which lies above, the ones which lie below. This part of the screen has some problem. I am having some problem to go to page. Page up is okay, but page down is second is pick up the leftmost and rightmost points So, this I call to be my P1. So, I am just releveling the points according to the sorted order. Now, what I will do is I will try to convince you about the computation of the convex hull for this upper half, and by symmetry it will follow for the lower half. Fine. Okay. Now, the points are relabeled as P2, P3, P4. So, this is the sorted order, right, sorted on the x coordinate P5, P6, this is P7, P8, P9, P10, P11, P12 and this is your possibly your P13. Fine, this is the sorted order on their x coordinates. Now, this algorithm what it would do is it would use rather let me not say it to start with, we will use some data structures, right. We will see what we use. Now, the idea of this algorithm would be as follows. Say it has computed the convex hull correct up to this point. Okay. For some reason, let me put this P7 a little. Now, see, when this P7 comes, then what you try to do is you try to extend this by including P7. Now, the idea is if you look at all points considered till now lie below this chain. Right. Now, P7 comes, I have to introduce P7 in such a way into the convex hull such that till now the same thing holds. Now, for this particular positioning of P7, this is fine, right. But say for example, P7 was not here, but somewhere here. Then this would have been your new hull and P6 should have gone away from the chain, agreed. So, to show to you further, so the story is something like this. I had this chain like this, a new point comes. So, I have to have this chain like this, right. And mind you, there is no point in this zone, agreed. Why? Because this point was immediate next point to this one. Okay. So, by some means I have to figure out that this new chain lies above this old chain and it should give the correct convex hull for. Now, look here, as because this new chain is always going by my computation is always going to lie above this old chain, then whatever points were in this zone, they are also below the new chain and there is no point here. So, that means the induction, I am not making a very formal argument for induction, but this induction would carry through, right, because the new chain should have all points below it, agreed. You can prove it more formally, but this is the kind of idea. Now, what I have to do is, as I said, I have to ensure that this new chain that I compute always lie above this old chain, right. how do I use it? Now, it can be so that your points are, your previous points were like this on the hull, right. So, what I now do is as follows. I look at, so I starting from this point, I look at its next 2 points, immediate preceding 2 points. So, this and this, okay. And I look at the line segment, the line joining these 2 points. If it is going to make a left turn to hit, so let me name them as say maybe P some P I, this is P I minus 1, this is say P I minus 2. So, if there is a left turn on this line segment P I minus 2 to P I minus 1, if you take a left turn to hit, if you are taking a left turn to hit P I, then the inference that I can draw is P I minus 1 has no business to be on the hull, right. But say for example, your your P I instead of being there was somewhere here, then it is making a right turn to hit P I, this line segment. This line segment is going to make a right turn to hit this one. So, I have to, given 3 points, figure out how I am making a left turn or a right turn. So, this is a geometric primitive that I should be able to compute. That given points say P 1, P 2 and P 3, how do we figure out left and right turns from line segment P 1, P 2 to P 3. Now, you remember area of triangles, right. So, sometimes if you had computed the area of triangles, sometimes it came positive, sometimes it came negative, right. So, remember this thumb rule of, right. So, essentially what you have to do is you have to compute the this determinant, and based on whether it is positive or negative, you can determine the direction, right. So, this is an exercise, I leave this as an exercise to you. See, I mean, if you argue on slope, there is some problem, because you have to do on the other side, then slope here and slope here would change a little bit, fine. So, allow it to do it, I mean do it using area of triangles. Okay. So, essentially if you look at P 1, P 2, P 3, so say P 1, P 2, P 3, right, you compute this area of this triangle. Now, say for example, if the points P 1, P 2, P 3 are collinear, then this determinant should evaluate to, right, fine. So, this is now this is a 3 cross 3 determinant, and you can compute this in order 1 time. So, in constant time you can figure out whether you are going to make a left turn or a right turn.
Positive means left.
I have to be, yeah, I think positive would be left and negative would be right. Okay. So, this basic primitive tells you whether you are going to make a left turn or a right turn. So, think of this as a black box. To this black box you give this coordinates p 1, p 2, p 3, it tells you whether it is a left turn or a right turn. You can very well easily design that black box, right. Now, if it is a right turn, you know that the last 3 points in your convex hull is pi, pi minus 1 and pi minus 2. But if it was a left turn, in this case, then you know that pi minus 1 has no business being in the convex hull. So, next what you do? You look at pi minus 1 has no business. So, then in business now is pi minus 2 and pi minus 3. Again you do the same thing, again it is a left turn, right. So, now you know that pi minus 2 also has no business being in the hull. You keep going back till you hit a point, right, such that this is going to make a right turn to hit pi, right. So, this is your, mind you, so now this is your convex hull, agreed. Now, try to think of a data structure that would allow me to implement this going back. Good. So, the data structure is stack. So, the order on the stack is top to bottom is right to left order of the point on the hull. Mind you, points which are below the old chain are never going to reappear on the hull, that is I am sure. So, in the stack I only store the points on the hull till now, but in a right to left order, fine. Now, look here how my algorithm is progressing. I had a pre-sorting which had the points sorted on their x coordinates, I had a stack, I took the first 2 points and put it on the stack, I had the third point, fine. I checked whether there is a left turn or a right turn. Accordingly, I reconstruct the hull, and because of this construction, I am sure that my new chain is always going to lie above my old chain, that is by construction, by my algorithm design has enforced it. So, all points are going to lie below, and I had already argued that in this zone, in this zone there is no points, right. So, by induction you can understand that this algorithm is correct. When do I finish my algorithm? The moment I have hit the last point. Okay. So, coming back to the algorithm steps, I had divided this, then use a stack to store the right to left order of the points on the hull, and in a loop pick up points from the x sorted order and construct the new chain till we exhaust all points on the upper half, and do accordingly for the lower half. the algorithm is clear to you? Fine. Now, let us figure out the time complexity of this algorithm. I have already spent an n log n for sorting, and then what did I do? I was putting points on the stack and deleting them. This is what I did. So, I had a sorted list on the x coordinates, and my loop is like marching on each point. So, it picks up a point from the sorted list, and when it is picking up, it knows that it has computed dealt with all points to its left, and it has a stack. It picks up the topmost 2 points from the stack with this topmost 2 points and this point with 3 points. It checks for a left or right turn, decides accordingly, right. If it is good, if it is a good turn, then this point goes onto the top of the stack, else 1 point from the top of the stack goes off. Again I pick up the next 2 points from the top of the stack, again I do the same thing. I keep doing till I get a bad turn, right, until I get a right turn, and then I stop, and then this point goes on to the top of the stack. So, if I go on the stack from top to bottom, I have the right to left order of the hull till now. Done? Now, so these are the steps. Now, see, first of all, I mean this you can do in linear time. So, these are the 2 steps, that is like we have to analyze a little bit closely. So, see, when I am doing this business, so when I encountered this point P I and I was going back through this chain dropping many points, right. So, in the worst case I might even drop close to a linear number of points, right. So, a fraction of n number of points, and this might happen many times. For each such insertion of a Pi, I might drop a sequence of points, right, because when constructing this new chain, by discarding this old chain, I have to drop, I might drop many points, right, and this might happen for each such thing, right. So, if I am doing the analysis without thinking of anything, this would go up to n square, right. For each insertion of Pi, I might have to delete a constant fraction many points there, constant fraction of n many points there. So, this can blow up to n square, but that is a very nasty kind of overcounting, right. Now, what I will try to do is I will kind of, how many of you know amortization argument for analysis? Can't you see an amortization here? See, whenever a point is deleted from the stack, see, a point is not going to go into the stack many times, right, only from this list it goes on to the stack, right. When a point goes off the stack, is there any chance of it coming back? No. So, now what you do is, instead of looking at these 2 nested loops, a loop that was going on the sorted list and inside you had a loop which was going on the stack, forget about this, forget about these 2 nested loops, rather think for each point. Now, for each point it can go into the stack once and can get deleted once. So, per point you are going to do only a constant many operations, there are n points in all. So, you are doing order n. So, essentially you took an n log n for sorting, and then this business of pushing and popping from the stack, if you count properly it is going to be n. So, in all you are doing n log n, and we are in business of hitting the lower bound of the problem of convex hull. So, this is an optimal algorithm for convex hull. and this algorithm has a formal name to it. It is, this algorithm is known as Graham's scan algorithm. Okay. So, the beauty of this algorithm is just this nice amortization that sits inside it. Okay. Our next goal would be to do the following. So, from this Graham scan algorithm we know that we have got an optimal algorithm for convex hull, right, because the lower bound of the problem was n log n and my upper bound or my algorithm has hit this n log n. So, I am in business, I am in have done an optimal algorithm. So, can I do something better? Say for example, in this situation, someone has told you that, well, on the hull there will not be many points. Say for example, someone has told you that there will be only h many points on the convex hull. So, now I will try to give you an algorithm which is function of both n and h. Okay. Yeah, we will see. H can h can be anything, h can be even order n. Then what I will say is that algorithm is not good, but if h is constant, I will show you a linear time algorithm if h is constant, right. Let us see. Again, let us go back to our earlier observation that I am sure of the point which is going to lie on the convex hull, right. I am sure of this point, this has the minimum x coordinate and so the technique that is going to be used for this is kind of known as gift wrapping technique. So, let us try to figure out the next point of which we can be sure. Further, what I do is as follows. I join all these line segments, right. How many such line segments? Order n, right. I look at their slopes. I take the one which is the smallest, right. So, it should be this. Now, what I did was, if you noticed, I looked at everything, right, and in a, so it is kind of a circular sweep around this point, and I hit the lowest most point, right. So, I drew order n such line segments, I picked out the minimum slope, I have got my next point on the hull, because if you think of a line through this, because if you think of this line, then all points are going to be on one side of it. So, it qualifies for a convex hull edge, fine. So, I have got one edge. How do I pick the next edge? Yeah.
Instead of picking that point like that, you can just push the point up.
Push the point up as in?
And then it will lead a right turn to take the.
I could not hear you.
So keeping that distance fixed.
Distance fixed, I mean points are fixed. So,
Yeah. No, like points are fixed, but I will consider a situation. Like the point we have just found out that the minimum distance point.
no, not the minimum, slope, angle.
Minimum slope we are finding.
Yeah. So, I looked at all the line segments, then this is the line segment line with the largest slope, and as I keep doing a circular sweep from it, I will go to a minimum direction, right. So, I pick the slope of an extremity, maximum, minimum, any one is going to be a hull edge, right. Now, I stand here, and again I do the same thing. Again you draw all these line segments, right. Now, in here that assumption that no 3 points are collinear helps, right, because otherwise 2 points would have the same angular order, fine. So, again do the same thing, then again find the circular order and you would get this point, right. So, now look here, standing at a point to figure out the next point on the hull, how much time do you take? N, and this computation you keep doing, and mind you, these computations you are only doing on the hull vertices, because until and unless you are sure of the next hull point, you are not doing any computation. You get there, you are sure that this point is going to be on the hull, and again redo the computation. So, you will keep sort of, the reason that it is called this gift wrapping is because you keep doing this computation till you come back to the point from where you started, right. So, at how many points did you do the computation? Per point, how many computations? N. So, total is order NH, right. Now, H can be order n, I do not discount that fact, H can be order n, then you are taking quadratic time, but if your H is something sublinear, so if your H is log n, you are doing n log n, if your H is constant, then you are doing order n. I mean, think of this situation when the convex hull is a triangle and all points are inside, right, then you have a linear time algorithm. So, this kind of algorithms which depends on an output parameter is known as output sensitive algorithm. So, this algorithm's time complexity is sensitive to an output parameter. Okay. And this algorithm has a name to it, good. Who said? Yes, good. This is known as Jarvis March. This is a nice algorithm, right, very simple, and if your h is small, we are in business, we are doing very good. Now, our next goal is, let us get even more, let us be ambitious, right. So, first one was n log n, next we saw nh, so this was Graham scan, this is Jarvis March, previous means Jarvis March. Yeah. Slope of the lines, right?
So, like in last in Graham scan also there was 2 points, 2 line segments. Why we are using triangle? We can find out the slope again, the smallest slope.
No, there is this positive negative thing, right. I have to interpret this left turn and right turn in a nice way. I mean, the point is, if you can figure it out in some other way, I do not have any arguments with you. The only thing that you have to make precise is that this left and right turn you have to compute in order 1 time in a correct fashion. So, this determinant is one way of doing it, you can think of other ways of doing it, right. So, yes, I mean, if you say that you know, no, that is okay, that is what I said, these two vectors.
Yeah, how are both different in last algorithm and in this algorithm? We are taking all, again in Jarvis method 2 lines were there.
2 lines, no, there are n lines,
No, for like we are going.
right.
We were finding the minimum of both.
Yes, I took all these n lines, right.
Yeah, but just to find for 2, I am saying this line and this line were there. How we are finding which one is smaller?
They have angles with the x axis, no.
So similarly we can take for the
Yeah, do it, I do not have any objections, but you have to convince me that way. See, essentially what, see here I am interested in the absolute angles, there I am interested in the relative thing to interpret a left or a right turn. There can be many ways of doing it. I gave you one simple way of finding the area of a triangle by using determinants, which can easily interpret by looking at the sign of the determinant whether it is a left turn or a right turn. Clear? Fine. Here it is absolute angles, if you might say so, right. This angle would be more than this angle, because it is an exterior angle to this triangle. Okay. See, this basic primitives you can compute in any way you like. The only thing is I need a constant time computation, a constant time correct computation, that is all. I think you should check this one. What? This one. Okay. Now, going back. So, any questions till now? So, next, what is the time complexity we can look at? Number of?
Does it become necessary to consider each point for calculating the slope? Like
Some of the points can go off, right? Okay, but then what is your hunch?
using y-axis and
No, tell me the hunch of your time complexity. That this is what we should aim at. Order of n, square root of n, but that beats the lower bound, right? N log n is, I know that n log n is the lower bound. possibly what about this? This is better, right? And this does not beat the, I mean it tallies with the lower bound, because if h is order n, then it is like again we are in business n log n, it is touching the lower bound, right. So, our next goal is this, okay. But in doing so we will use, it is kind of a nice algorithm which was a paper by a very great computational geometer Timothy Chan, and if I remember correctly it was in the 1990s. So, it is an algorithm of recent vintage, mid 1990s if I am correct. Now, look into this fact that n log h is faster than both n log n and n h, right. But the idea of Timothy Chan is it will combine these two algorithms in a nice way, two slower algorithms in a nice way to get a faster algorithm. Seems counterintuitive, but that is the beauty of the design. Okay. But before going there, let us look at a very basic thing which is kind of follows from your high secondary days. Let us look at a geometric series. And assume your R is greater than 1. So, what is this sum? R to the power of agreed. Now, if you are interested in the asymptotics, this is of the order of r to the power of n, right. Okay. This has an interesting story. So, this is telling you that in a geometric series, if you are looking at the asymptotes of a geometric series, it is the last term that dominates the previous sum, right. An interesting consequence is, look at a complete binary tree. Let us start from the very basics. What? Big O you do not know? So, you do not know this big O notation? You have you come from a computer science background, right? You come from what background? No, in your undergraduate what are you studying? First year in what? Huh? Oh, acha. You have not done a basic discrete maths course, no? Okay. So, big O is something like this. Let me tell you very simply. So, if I have a function f n, I would say that it is big O of g n if there exists positive constants So, this C has to be a positive constant such that for all n greater than n naught. So, important to understand in this definition is these two positive constants. C and n naught, right. So, what does that tell you? That there is an n naught, okay. So, in this zone these two functions can do anything they like, but beyond this C g n should dominate f n, right. Then I will say that f n is big O of g n. So, say for example, n square is big O of n square, right. N square is big O of n square log n. N square is big O of n cube, right. So, any function that dominates it beyond an n naught with a positive constant c. Important is, though I have not written, important is that this c and n naught are positive constants. Okay? Right. So, now let us come back to this. Now, you understand? Okay. Now, you look at this binary tree. How many leaves are there? You are looking at a geometric series like 1, 2, 4, right, and that is what the story is there. This dominates this sum, right. You can think of even increasing it, right. That is the story, that your number of leaves in a complete binary tree dominate your number of internal nodes. This actually follows from this idea of geometric series, that in a geometric series it is the last term that dominates. Fine. So, I will use this idea to design our next algorithm of n log h.